All right, hello. All right, here we go. All right, so nested structures. How many people here have used nested structures? All right, a good deal. So I hope I don't disappoint. So this is the slide just to say that I know what I'm talking about. So I wrote a book. I used to work for a company called FINRA. If you haven't heard about it, they, if you're financials, you'll hear about it. They categorize all the data from the stock markets and to these large graph databases. And then I worked for this vendor called Cloudera. I did that for about 4 years, worked for about 100 different companies or so. And now I'm the technical group architect for Blizzard, doing all their data, cloud, and tests. And I contributed to a whole bunch of projects. Has anybody ever played a Blizzard game? All right, there we go. All right, so if you don't know Blizzard, Blizzard makes World of Warcraft, StarCraft, Hearthstone, Overwatch, Here's the Storm, and that says Here's the Store, Diablo, and it's part of Activision, so underneath there is also Call of Duty and Candy Crush. So if you play video games, you probably have interacted with us one way or another. And it says over there that we deal with over 100 billion messages a day. There's a good chance we're going to pass 1 trillion messages a day very soon. So we deal with a lot of data. Okay, so we're going to talk about nested structures, use cases for nested structures, and some code samples, depending upon how much time we have. So before we get started, just really quick, in the world of Spark, right? I'm echoing a whole bunch, but in the world of Spark, we have these things called RDDs. But just if you're not familiar with it, you start with a collection. An RDD is a collection that is partitioned, immutable, and deterministic, right? And then you have your data frames, which are, in the old days, they were RDDs that have type row and have a schema. Nowadays, they're data sets. And then there's data sets, which essentially you can put case classes in there or row objects in there. And they have benefits over traditional RDDs. Now, when we talk about nested types, we're going to be talking about content that is in one of these little cells here. One of these, either a case class or one of these type of rows. All right, so what I'm going to do is I'm just going to walk through how do you make some nested types and how do you interact with them first. So first we'll go with JSON. So JSON is a really easy nested type structure that a lot of people will know. Here's our example here that is a group, time, value, and nested. And what we see here is inside nested, there is column 1, column 2, but you have multiple rows, right? And if you haven't done this, you probably did this because this is littered through the examples of Spark, is you can read that JSON in, and when you write it out, you can see that it's a row that has a value in it, but it also has a wrapped array in it. And then, so you have your top level values and you have your nested values. Now, one of the things that I love about Spark and not love is when you write this way, it's rows of rows, but when you read, it's rows of wrapped arrays. But you can go and view those. Now, you can even query those. You can make that JSON a table, and you can access that data by saying accessing a group, which is a top level element, and then you can access the nested column. But when you access it this way, you'll still see that it has the entirety of that nested column 1 returning to you in a wrapped array. One of the things you can do is you can do a lateral view on the nested column, which will flatten the data out like if you were doing a denormalized view, right? So we're going to go back in a little bit to talk about the difference between a denormalized view and nested in a little bit. The next way that's very popular of making nested tables nested data sets is with tables. So you can look over here on the side. This is how you would make a table with nested structures, and this is how Hive works today. And what you'll see is, we have our first 2 columns, A and B. Then we have a nested structure, which is called nested. And then we have 2 columns in there called C and D. You can definitely go and say this is just an array of values. That's totally legitimate. And you can also just say that it's a strut. But in this scenario, we're going to do an array of structs, right? Now, if I was going to parallelize that structure, you would do the bottom thing, right? You would see here I have rows of sequence of rows, all right? And that would parallelize that and turn that into a RDD. But now I need a schema. And there's two ways that I typically go about getting the schema. The first is I query the existing table and I say limit 0. And what this is going to do is this is going to execute extremely fast because it's not going to do anything. But it's going to return me a data frame that has a schema. And from that schema, I can now make that RDD into a data frame. If you don't want to do that, if you want to just stick with code, so if your table doesn't already exist, you could use struct types. But in this area, you have to understand that you have a struct type of struct types. And it works the same way. It gives you a schema. You can create your nested data structure. Last one we'll go over is a new one with data sets. And it's this idea of using case classes. So here we have a group bean and a nested bean. And our group bean contains our nested bean objects, right? And we can read that same JSON in, and now we can say as a group bean. And now we can have compile time stuff like .group and .time. Whereas before, if we had rows, we had to say get as string, and then you would have to put the word group in there to get the value out. And you wouldn't know if you ran into a problem until runtime, right? And you can do the same thing in terms of SQL and making these tables as such. And it would look like this in terms of its schema. So before I go to the use cases, any questions on creating nested types? All right, so typically they're just objects with objects inside of them. Use cases primarily that's really important is parent-child relationships. If any of you have been in big data for any time, you would have recognized that joins are one of the most painful things you can do in big data. And Spark has definitely tried to make this simpler, but the reality is physics are not on our side, and we have to serialize data over the network, and it's terrible. The other one is doing n-grams. So if you're not familiar with n-grams, it became popular when you're doing indexing words and stuff for search, for things like Lucene and search platforms. And the idea is words that are next to each other or in combination is more helpful for indexing and finding things than individual words themselves. And this also has a lot of value in our world. If you can imagine, we have a card game, and cards played together have value together that one card by itself might not be as valuable. The other is this concept of group by keys and windowing, right? So let's first talk about the join on read. So joining parent-child relationships, if you had a situation where you had a credit card and transactions, if you had a table that was all the credit cards and all the transactions, joining that table would be pretty expensive depending upon your clientele. But if you had them nested, the join essentially would be free. And it's because of the way it's laid out on disk, right? And the other nice thing is there are data structures today like Oric and Parquet that when you ask to read either the parent table or the child table, you only deserialize that table. So you can don't have to read the entirety, but also aggregations in such a way they can be done locally. They don't have to require any kind of shuffling or whatnot. And for those earlier on, I was talking about we're going to show denormalized versus nested. You can see here if we're in a nested data structure, we actually store less data, right? And so this is the same in memory as it also is on disk, right? So especially as we start to get to things like Cartesians, you can imagine here we are storing a lot less on the one side of the Cartesian join if we're using a nested structure. Now the downside of this is the way this is actually stored both on file and both on disk is there's some limitations. If you have unbounded children, you're going to run into a problem. And it's because in memory, you're going to get the entire top record in one shot. So if you have over 1 million children per top record, you could run into out-of-memory exceptions, right? I mean, depending upon how much memory you allocate. But also the way it's written on disk. You can see here, this is how Parquet describes itself on its README page. And what you can see is there are row groups, and row groups have columns, and columns have pages, right? And the big thing is row groups have a particular amount of size to them. And the reason is because The way columnar file structures are written is you have to write the entire row group out at a time. What does that mean is you have to actually cache that in a buffer before you write it, right? So if your children are too big, you're not going to get many rows, top-level rows into a row group, or you might even run into trouble populating a row group because you'll run out of buffer space. So an example here, you can see the typical setting for a row group is 1 gigabyte. So if you have children in a record that is over a gigabyte, you're already starting to run into some issues, right? But hopefully you don't have that many. And we're talking about it a little bit, but there's some tricks you can do. So let's say you talk about credit card transactions, right? So you have a card and transactions. If you realize that you could run over 10 million transactions for a credit card, what you can do is you can make that top-level element not the credit card ID, but you can make that top-level element the credit card ID and the month, and the day. And the idea there is you can still do roll-ups and joins at the month or day level very, very quickly. But across days or across weeks or months, then you would have to do some kind of join. And we're going to talk about it a little bit more, I think, later on, is this concept of bucketing and sorting. And if you did that, it would be merge joins all the way up. And if you're curious on this one, page sizes also have sizes here. And that at least allows you to do some type of indexing to do less reading when you're looking for particular values. Doesn't really apply too much for us in our use case, except for, again, when you have very large children, you might not be able to take advantage of that feature. All right, so the big problem is, like, how do I update? Let me see if I show a diagram. I don't. Oh, yes, I do. So how do you update children? So the whole problem, the whole benefit of this thing is you can join and aggregate very quickly. The problem is it's very difficult to mutate children, right? So if you had transactions and you wanted to add transactions, how would you go about doing that? One trick that I've done is, you could always do a mega join and rejoin and rewrite everything, right? The other one is normally your existing data is set. And if you can organize that in a bucketed and sorted manner, and if you're not familiar with bucketed sorting just means you partition by something and then you sort within the partition. If you do that bucketing sorting, when you add the new data set, you only have to shuffle the new stuff, and then you can do a merge join on the old stuff and the new stuff. This, at one place, took a job from, I think it was 36 hours down to like 40 minutes. So again, trying to remove shuffles. All right, and again, I talk about we can also decrease our parent by adding something extra like a time, so that if your data is append only and not mutable, you'll run into this problem less. You'll just be always appending nested structures. Any questions so far? Am I going too quickly? I only have 10 more minutes. I'm trying to get through a lot. So the idea of n-grams. So think about the Netflix use case, and you wanted to figure out what combination of movies are most popular, and then can I categorize people by combination of movies in terms of n-grams and stuff like that. And what it comes down to is it comes down to a Cartesian problem, right? So if these are all my favorite movies, right, what you'll find out is if I did the traditional SQL join, I would generate all those values on top, right? Then if I realized I don't care if it's, I don't care if it's 1, 2, or 2, 1, and I can do ordering. So already there, I can decrease my data footprint pretty dramatically. But then if I apply nesting on top of that, my Cartesian join is now much more, bearable, right? And it's still bigger than linear, but it's not going to be that painful at all. And this can be repeated for 3 n-grams or 4 n-grams and stuff like that. It also, the other thing that you can notice here is there's only 3 records going out. So when you're doing the reduce by key, the whole idea of reduce by key is the more that you can keep there and you do your aggregations on your executors and less has to go over the network, the better. So this also helps the reduce by key algorithms there. And I have code for this if we want to go through it. And you can see here as we add more records, this is with more records, it becomes even more prominent that you want to start doing the nested structures. Does anybody have Cartesian joins? Anybody have any? Okay, a couple people. Cartesian joins suck. Yeah, and we talked about using reduce by key. And if everybody's familiar with reduce by key, the nice thing is that you only keep 2 records in memory at a single time, and you can reduce and transmit those across executors. Okay, so nested structures, we're talking about nested structures, and that's the whole idea of group by key. So the whole idea of group by key, right, is you have one key and then you have everything that was grouped by in it. And it follows the same good things and bad things that nested structure has. If you have Skew in your data set and you get a really big group by key, you're going to get an out of memory exception, right? But they're very good for things that are so advanced windowing and standard deviation, anything where you need to go over your data multiple times. So if you do find that you have Skew, you'll want to break it down more than just entity. Maybe you can break it down by time range. And what I mean by time range is you could group an entire week together, and then you would double send Sunday. Like you could send Sunday to be processed over here and Sunday to be processed over here. It's just on this side, we use it just for stuff that travels the gap, right? And this can allow you to do group by in a safe way. And again, we're repeating the same thing, the ID plus something else like a time range to protect yourself. I don't know if I have time to go to the code, but if we do, we'll go into it if you have questions. The downsides and things to care about. So we talked about this a lot. Size of children is a big one. Mutations, we've talked about. Adding top-level groupings. Try to stay append only and merge solutions other than that. And wow, I finished a little bit early, so I can start to go into code. Which one do you guys want to see? Do you want to see the Cartesian, the n-grams, or do you care to just see the creation and stuff like that? So n-grams, raise your hand. Okay, we'll do, what about just creation and stuff like that? All right, we're going to do n-grams. All right. Let's see here. Many to many. Okay, so if we were going to do just regular joining, right? We would go through, and this would just do the ordering. We're going to go through and we're going to iterate through the list once. And then we'll iterate through the list again. If value 1 is less than value b, then add it to the list, right? And this is how you would do that second level, the ordering Cartesian. And this, if we wanted to do the nested Cartesian, we have to do something a little bit extra. We're going to add a little class here called nested counts. And what's going to go in here is this is going to have a key and counts, and we're going to be adding this to a hash map. And what we're going to be able to do is we're going to extend the plus operator and this is a string to just show it, right? And what this is going to do is any of the keys that came from the previous, if we join 2 of these, so if we're doing a reduce by key, they will merge their results together. And you can see up here as we create it, and I'll try to debug through this so you can through the steps in a second. Again, we go through the loop, and we do a for each on the A, and then we do go through the loop for the for each on the B. The difference here is we are going to make a nested structure for the A. We're going to add all the children in, right? This is the value B and 1s. Let's say we're doing a count, right? And then we return that the thing that's going to come out of our flat map is our key is going to be value A, and our value is going to be all the structures that are in, all the B's that are associated with A, right? And what this is going to do then is we'll just simply do a reduce by key that adds them together like this, and we can print out the results. And again, this will get us that smaller Cartesian than the big one, right? So let's see if I can, if I still have the parameters set for it. Is it going? Oh yeah. Okay, so those are the results, right? But let's dig into it. How many people knew that you could debug Spark? All right, so for those who don't know, you don't actually need a cluster to run Spark. All you need is a JVM And you can just hit like debug here. And you'll see that I can stop inside my Spark without a cluster and actually can see what's going on. So you can see here value A1 is value of 1. And then you can see that this hash map contains a 2, a 4, a 7, and a 10, right? And you can see here this one's a 4, a 7, and a 10. And if you're wondering, this is what the data looks like. It's A and then all the actions you can possibly have, right? And what we're trying to do is the combination of those values. And then again, when we can go to the very end, and then we can see here, 4 has 5 and has 7 and 12 and stuff like that. This one, number 1 has the most, right? It has 2 4 combinations. It has 2 7 combinations. Very cool. All right, and I have 4 more minutes before I can ask for questions. So let me quickly go over a use case for JSON, and then also we can go over struct types. So this will run it, and then we'll do some debugging. Oh, one thing that's different about the both of them is about, I don't know if you guys know this trick too. If you don't put these in, then it becomes almost useless. Zoom in, yes. Those are, remove the Spark logging. But if you ever try to figure out what's going on in your Spark application with that on, it's kind of confusing. So I always leave those off. All right, any questions so far? All right. No. I can't see. OK, no questions, I guess. So in here, we'll just debug the JSON. And this JSON is reading from nested JSON here, which is group, time, value, and then nested like we had in the demonstration. And you can see down here, every single row has the, I don't know if you can see that. Every single row has the schema, the full schema, and the full values with the nested types. And then you can go down and see all the different values. Any questions on that? All right. So I guess I'm finishing up. Unless there's any other questions. No questions. I guess nested types is boring. I apologize. But in general, yeah, parent-child relationships, Cartesian joins, or windowing, very powerful. So that's pretty much it.
All right, we've got 7 minutes. Anybody want to have a question? Did he completely mesmerize you? I hope not.
I'm supposed to put it on my Git. I just haven't gotten to it yet, but it'll be on, I have 2 Gits. There's one that's like, I think it's like Ted Bear 42. It'll be on that one. This is, all this code right here is from a training class I'm doing with O'Reilly. So O'Reilly has like these training classes people can subscribe to. And I have it's a 3-hour course about everything you want to know about mastering parallelism with Spark. And then this is just a bunch of little examples like salting for partitioning, custom partitioners. We do small, medium, and big size windowing operations. And nested structures plays a big part of all of these, really. And then Cartesian joins and stuff like that.
All right, there you go.
Hi. So you mentioned nested types in Parquet. I was wondering if you had any insight about nested types and data sets and serialization, deserialization to say like Spark storage or on disk, if that had any effect on performance there.
So when you say Spark storage, what's a Spark?
Like if you were to cache a data set in memory rather than saving it to Parquet.
Yeah, if you're going to cache it to memory, I believe that when you do cache data structures, they are stored columnarily inside Spark. But I believe that's also configurable. The main advantage to storing things columnarized would be if you were going to compress them. And and the reason for that is the entropy is lowered if you compress a column per column as opposed to a row per row. But if you're storing your RDD in memory and it's just solid memory, There probably wouldn't be too much benefit from that unless you were, yeah. But last time I checked, I believe that's configurable, how you actually want it to be persisted in memory.
Yeah, I mean, you can specify an option whether you want it serialized or deserialized.
Yeah,
while you're caching.
Yeah. And if you're serializing it, it's probably going into a columnar format.
Right.
But once you've serialized it, so this is a big misnomer. So people will tell you memory solves everything. If you serialize it in memory, there's a really good chance that when you retrieve it, it'll probably be almost as fast, maybe a tiny bit faster than reading from disk. But the majority of the cost is not reading it from disk. The majority of cost is serializing it. So.
Similar question. Have you had any luck with nested types with Java objects internally in like a data set?
With Java objects internally. So I do most of my stuff through Scala. So I haven't done Java in a while. Just because
you do it through Scala as well. I'm talking about just any kind of Java object that isn't string type, integer type, et cetera. Any kind of complex, any kind of non-base type, I should say.
Different than the case classes I put up there, or you're saying just making POJOs?
Yeah, POJO, throwing it into a data set.
Yeah, I mean, I definitely did those before. Thinking now about the case class implementation, I don't know what the advantage of would be doing those before. Before, I would do that type of stuff in RDDs. So back in the 1.4, 1.5 timeframe. If you know of any reason why case classes can't substitute that today, let me know. But I think it's everything that you had before, but now you can have a schema on top of it, and now you can run SQL on it.
Thanks.
Any other questions? Could you go to the mic, please?
Hi. So most of the real-world data is not nested, right? So is it worth doing the nested structure for the real-world data to do the analysis?
So there's two parts to the question. One is real-world data is not normally nested. And I would argue that real-world data is almost always nested. There's parent-child relationships with everything. Now, what you might be referring to is real-world data in terms of a relational database.
Correct.
Now, in terms of a relational database, you're right. Everything's in tables, and there's parent-child relationships and stuff like that. But the reality is relational databases, structures, don't work at scale, at large scale, without lots of money. So if you have lots of money, you have no problems, right? Well, until you have problems, right? I mean, at some point you will run out of money. But if you're like in the cloud, or if your company actually cares about a budget, or you want higher concurrency, you'll want to try to find some of these patterns where more of the problems are solved with the storage layer as opposed to the execution layer. So, I mean, there's a big talk that I do at Hadoop World, which is about if you master your storage layer, your execution layer becomes less of an issue in terms of concurrency. And those are things like using time series databases for counting instead of aggregating and stream processing, or using nested structures to avoid shuffle joins, or using things like Lucene as a great way to cube very recent data, as opposed to always using a hammer, which is, and I know we're at Spark Summit, but Spark is a tool, and it should be used for what it's good for, but it shouldn't be used to solve everything. At least that's my opinion. So.
Any other questions? We've still got a minute and a half. All right, if none, then give a big welcome to Ted.